All right, distribution of cardiac output. Where does blood flow go as you transition from rest through different levels of exercise? Cardiac output goes up, but then by changing radius of blood vessels, radii of blood vessels, we can determine where the blood goes, right? Which tissue gets the most blood flow during exercise? Which gets the most or the highest percentage of your cardiac output during exercise? Skeletal muscle. So as you go from rest to low to moderate to maximal levels of exercise, blood flow to skeletal muscle goes up. Blood flow to the myocardium, heart muscle, goes up as well. Okay, what happens to, let's say, blood flow to the kidney and blood flow to the stomach as you go from rest to low to heavy to maximal exercise? Blood flow to those areas goes down. Even though cardiac output, let's say, is going from 5 to 25 liters a minute, so you're increasing total blood flow. Despite that, blood flow to those organs goes down. What's the reason why? Parasympathetic nervous. Not exactly. Not exactly. Okay, we'd much rather send our cardiac output where? During exercise, we'd much rather send it to skeletal muscle. And it's kind of, again, I talked about like an evolutionary response. If you're being chased by a critter who wants to eat you, would you rather be digesting your dinner or filtering your blood, or would you rather be sending blood flow to your skeletal muscle so you can outrun the critter? Remember that? Okay. Same thing kind of happens, though, in response to blood flow to the skin. What happens to blood flow to the skin as you go from rest to light to heavy exercise? Blood flow to the skin goes up. Okay, now you think it kind of sounds weird. We're not sending blood flow to the kidneys and the stomach, for example, because we'd rather send it to the muscle. But why would we preferentially send more blood flow to the skin during exercise? It is to thermoregulate, to cool off. Remember that? Okay, your skin is essentially like the radiator in your car. By sending blood flow to the skin, you can dump heat to the environment. Does that make sense? But when you go from, let's say, moderate to maximal levels of exercise, what happens to blood flow to the skin? It goes back down again. So it increases until you get to maximal exercise, then blood flow to the skin goes back down again. And the reason why is because at maximal levels of exercise, we end up sending that blood flow instead of to the skin, we send it to skeletal muscle. I use the term there's a tug of war between the muscles and the skin at maximal exercise, and who wins? The muscles win. Okay, remember that? Okay, let's talk about control of heart rate for a minute. There's 3 things that control heart rate. Do you remember what they were? This could be a good short answer question. Hormones is one. Sympathetic and parasympathetic nervous systems. The sympathetic nervous system does what to heart rate? Makes it go up. Okay, so that could be an increase, decrease, or stay the same. If we had increased sympathetic nervous system outflow, heart rate would increase sympathetic would make it go up. Increased parasympathetic would make it go down. So parasympathetic nervous system slows down heart rate. So when we talk about elite endurance athletes at rest, have a heart rate that is what compared to normal individuals? Lower heart rate at rest. What are the 2 reasons why? Well, their parasympathetic nervous system is more activated. Okay, we say they have greater parasympathetic drive. Okay, what's another reason why? What did we say was the difference between cardiac output at rest between an elite endurance athlete and a normal individual? It is, they're both 5 liters a minute, right? They're the same. But what do we know about the stroke volume of an elite endurance athlete at rest? It's higher. So if cardiac output's the same, stroke volume is higher in an elite endurance athlete, then heart rate in response has to be lower. Those are the 2 reasons why. We doing okay so far? Questions? Okay. Blood components and measures. What if I said define hemoglobin? Define hemoglobin. What is it?
Protein carries oxygen.
Yeah, it's an iron-containing protein that carries oxygen in the blood. Okay, what are the units on hemoglobin? What are the measurement units? If I want to measure how much hemoglobin you have, as a funky measurement unit. Grams of hemoglobin per deciliter of blood, or 100 milliliters of blood. Same thing.
Can you write that out?
Sure. It is grams of hemoglobin per 100 mLs of blood. Okay. Give me an average hemoglobin value for a normal male. Typical hemoglobin value for a male. You know the units, grams of hemoglobin per 100 mLs of blood. Okay, about, I'd say around 15, give or take, grams of hemoglobin per 100 mLs of blood. Women would be slightly higher, lower, or the same. Women would be slightly lower. I'd say an average value for a female might be about 13 and a half, give or take a little bit. Okay, what if I said define hematocrit? Define hematocrit. It's the ratio of red blood cells to, okay, it's not, technically it's not red blood cells to plasma, it's red blood cells to total blood volume. Red blood cells to total blood volume. Okay. What are the units on hematocrit? Percent. Okay, so give me a normal hemoglobin value for a typical male. Say about 45%. Females are slightly lower, I'd say around 42%. Okay, if your hemoglobin values are lower than normal, we say you are anemic. The Fick equation. What if I said write the Fick equation? Write the Fick equation. Do you remember what that was? VO2 equals cardiac output times AVO2 difference. AVO2 difference. So remember the V is special. It has that little bar above the V. What does that bar stand for? What's that? Mixed stands for mixed venous content. And there's a special reason why we say mixed venous content. Let me ask you this. If I'm doing an exercise bout, if I sampled blood from a vein in my hand and a vein in my leg, would the oxygen contents be the same? The answer is no, they'd be different. So if we want to get a picture of what the average venous content is for all the venous blood in the body, we'd have to wait till all the venous blood mixes together and pools together. Where's the one place in the body where that happens? Happens basically on the right side of the heart, okay, before it goes into the lung. Okay, so if we actually want to measure mixed venous content, that's where we'd have to measure. Let's talk about an artery. Let's say I'm doing exercise again, I measure from an artery in my hand and an artery in my leg. How would the oxygen contents compare? It would be the same. Oxygen content in an artery is always the same. Okay, so one way that you can increase your VO2 is you can increase cardiac output by just looking at the Fick equation, right? It's cardiac output times AVO2 difference. If I increase cardiac output, that would increase VO2. More blood flow, more VO2. What would I have to do to AVO2 difference to increase VO2? AVO2 difference would have to get bigger.